that introduction to entropy. This will be for our first topic for this semester. And the references that we are going to use is that the book by Chengel and the Bowles, and also we'll have the additional reading by the Klein and Nellis, and as well as the Knapp. The roadmap for this semester is that we will talk about entropy, okay, and then the exergy, which will be this one is the chapter 6 and the 7 together. Some parts of the chapter 6, this one will be a review, okay, but mainly it will be chapter 7. And then I will talk about the exergy. This one is under question mark, but because if we have time left, we will talk about the exergy. And then I will talk about the power cycles, and mainly we will talk about Otto cycle, and then diesel cycle, and also Brayton cycle. And vapor cycles, which is famous one, is the Rankine cycle. And the refrigeration cycles, talk about the different refrigeration cycles, and then psychrometrics. And for the psychrometrics, this is mainly important for the HVAC and heating, ventilation, and air conditioning. Here we are talking about the humidity, that is the psychrometric chart to find the related properties of air. And then renewable energy. This will be the last part of our plan for the semester. So for today, we will review thermodynamics 1 and derive entropy in mathematical form. Okay, this will be the 2 important steps for today. Okay, that the thermodynamics, if you know that saying 3 words, it will be that energy, equilibrium, and entropy. These are the main important topics in thermodynamics. And the energy, if you remember from the first course in thermodynamics, the first law defines the different types of energy transfer and the conservation of energy. And equilibrium is the essence or cornerstone of thermodynamics, because whatever thermodynamic device that you are analyzing, it should be in equilibrium. And the entropy is the topic of thermodynamics 2, and of course today's topic. And here we have a heat transfer. This is a simple example. There is a heat transfer to a rigid container. You can see that the boundaries of the container do not move. And if I write the first law, it means the first law says that the internal energy and the plus kinetic energy and the potential energy change of the system, that will be equal to total in to that system minus total out from that system. And the in and out properties, this can be any transfer properties. It can be by heat, it can be by work, and it can be by mass. Similarly here, it can be by work, heat, it can be by work, and it can be by mass. And for most of the thermodynamic devices, this kinetic energy and potential energy change are not so important. And for the mass transfer, mass can carry with itself, that is internal energy, it can carry with itself the flow energy, and it can carry with itself kinetic energy and the potential energy. Okay. These are the types of the energy transfer that can be carried with the mass. Similarly, for outlet, you will have that kinetic energy, you will have that potential energy, and you will have that flow energy with internal energy. This combination property, we call it as enthalpy H. And I will do that first law analysis for this system here. You can see there is no work transfer, there is only heat transfer here, and therefore the delta U of the system will be equal to Q in. Now I'm doing the similar internal energy change, the same internal energy change. It changed from U1 and the U2 here due to heat addition, but now I'm changing internal energy of the system by adding work. Okay. I'm adding the work, but the delta U system and delta U system, these are same. Okay. Same delta U. That internal energy of the system in the first case changes only due to heat transfer, or I can do the same stuff, but I'm now adding the work transfer to the system and the change in the same amount of the internal energy. And the now question comes, if we take these delta U's, since they are same, and it will be that Q in is same as work in. Okay. And this is the problem of the first law. The first law doesn't put any, any difference between heat and the work transfer. The first law says that you can change the internal energy of the system by heat transfer and the work transfer in the same manner, and it doesn't put any difference between them. What is the difference between heat and the work? There you cannot see any difference from the definition of the first law. But the first law is all about, this one is all about quantities. Why it is all about the quantities? Let's give one example here. Say that U2 minus U1 is 10 joules. This internal energy change in 10 joules, it can be done in any way. It can be heat transfer, it can be work transfer, it doesn't matter. Okay, at the end, you should have this 10 joules. Okay. And it is all about the quantity. If you have the balance between left-hand side and the right-hand side in terms of values, and then it is okay for the first law. Okay, now we will have one more review part here. So I have a power supply with a 10 volts with a resistance of 1 ohms, and the work power. Okay, power is that I into V, and the current into the voltage. And instead of voltage, you can write that current multiplied with the resistance. You will have that. Sorry, I should do the opposite here because the voltage is known instead of the current here. Okay. And instead of the current, I can write the voltage divided by resistance, and therefore you have one more voltage here, voltage squared by the resistance. And we have the 100 volts, and you have the 1 ohms, and therefore 100 watts. This is the power supplied to a system here. It can be battery, it can be any other system. And this power supplied to a resistance of 1 ohms, this is a resistor here, and this 1 ohm resistance power supply is dissipated as heat. This dissipation is the same as the work transfer. If it is steady, then you will have the left-hand side is, for this part is 0, and right-hand side will say that total in should be the same as total out. Total in should be the same as the total out. For our case, there is only one in, which is work in, and this work in should be dissipated, and dissipation will be as heat. Therefore, these two quantities will be the same. Now, let's see the opposite. Now, what I am doing is that I am adding the heat, and there is 10 volts and 1 ohms, the same stuff, and I'm trying to get the 100 watts. And if I say that this is steady, okay, this is the resistor, okay, resistor. Same resistor here. I'm heating the resistor, and I'm expecting that I will get the 100 watts back, 100 watts back. And if I write the first law, if it is steady, then that Q dot in should be the same as work dot out. And if steady, this one should be true, because I have the left-hand side as 100 watts, and the first law doesn't put any, that constraint on the right-hand side. It doesn't put that it should be work, it should be heat, it should be mass. Okay, it doesn't put any constraint. You can select any of it. At the end, it is about the quantity. If the quantities are okay, if the left-hand side and the right-hand side are equal, then no problem. Okay, I do the same stuff here, and I want my output to be work dot out. It is not a problem from the first law point of view, because first law talks about the numbers. It's not about the quality. The first law doesn't put any direction, okay, directionality of the properties. It's all about the balance. If the left-hand side and the right-hand side are equal, you are free to select any right-hand side property here. And this one should be equal to 100 watts. You see, the first law says that if you hit the resistor, you can get the 100 watts. Okay, that is what first law says. You can see the problem. In reality, it's not true. In reality, if you hit the resistor, you cannot get the power. Okay. You can put some arrangements, different arrangements here, but you will not get this 100 watts back. Okay, at the end, you will get some small watts by using Peltier effect, okay, this thermodynamic cooling effects. But here, this is impossible. Okay, this is impossible, and therefore, however, the first law doesn't say. First law says it's possible. Okay. In reality, it says no. So now we have come a point where the first law is okay about the quantity, but it fails in quality. So from the quality, we can feel that work has better quality than the heat, because I can get this 100 watts as a heat, which is used as the electric stoves, electric oven. So you have the same electric oven here, and you get 100 watts and the same as heat. Okay, that is what it works like. But in the opposite case, from the first law point of view, it is possible. But in reality, it is not possible because, as I said, you can put different mechanisms here. You cannot get this 100 watts back in reality. Therefore, the quality comes into picture. And this quality will be in terms of the second law. Okay. You will see that second law puts a limit on the properties. And so what the second law says, let's see that. There are two statements for the second law of the thermodynamics. One is the Kelvin-Planck statement, and the other one is the Clausius statement. Kelvin-Planck statement says that it is impossible to build an engine. This we are calling this one in thermodynamics a heat engine. It will operate in a cycle and will give net amount of work with a source of single reservoir. We'll show one example here for you. This is the heat engine. Have the heat source, so it can be for example, car engine. One example. So you are burning the fuel, so the heat comes from the combustion of the fuel, and then there is a net work output from the car, the motion of the car. And you are having also the exhaust part of the car. This is the system. But the Kelvin-Planck statement says that this system without exhaust, without this one, if you don't have this part, okay, the second law says that it is impossible. Okay, there should be always the exhaust system. In other words, there should be always the heat rejected. If you have heat addition, if you have work output, heat rejection should be there. Without heat rejection, this cycle is not possible. Okay, this is the Kelvin-Planck statement, what it says. There cannot be an engine operates in a cycle, but with a source of single reservoir. You cannot have one single reservoir as it is here. So you cannot have this one, and you will get the net 100% work. It is impossible. And the second one is that it is impossible. This is the second law. It is impossible to build a device, and some books put that part, and some books do not put it. Okay. And some books say that the cycle part is not important, the general device, but some books put the cycle term here. That it is not impossible. It is impossible to build a device that will transfer the lower temperature energy to higher temperature without any work input. Let's see that one. Okay, now this one is the refrigerator at our home, okay, or air conditioner. What the refrigerator does is that it cools the room, or it cools the food. This part is the food. Okay. It takes the energy of the food, the QL, and rejects to the environment. This is the QH. And this Clausius statement says that a refrigerator without this one is impossible. It cannot be that there is a refrigerator that transfers that heat from the food to the environment without any heat, without any electricity. So that, let me summarize in simple terms, the car engine without exhaust is impossible. This is the one part of the second law, and which is the Kelvin-Planck statement. And Clausius statement says that the refrigerator, this is the one example, air conditioner, any heating and the cooling systems, that is without electricity is impossible. Not heating, that cooling systems. Okay. Any cooling system without electricity is impossible. You should have always electricity or work that in. This is the two important laws of the second law. And you can see that these laws are, that they don't seem like scientific, okay? But you will see that in the next examples, these laws are very fundamental, and that these are the implicit definition of the entropy. Okay, these are the implicit definitions of the entropy. And if we summarize these second laws here, we can feel that there is these two second laws put some constraint. Okay. So you will see that this constraint is implicit definition of the entropy. It puts the constraint that you should always have the exhaust system and you should always have the work net in. Second one is that however, these two laws are assuming that they are separate, but they are complementary. So what if one of the devices, that violate Kelvin-Planck statement, it will also violate the Clausius statement. It's not possible that the device violates Clausius statement, but it is okay with the Kelvin-Planck statement. It is complementary. Okay, one that violates Kelvin-Planck, okay, also violates the other one, the Clausius statement. Okay. And the third one, it is about the efficiency, and the third one says that, so if you don't have, so we will see in the next slides that 100% efficient device is not possible. 100% efficient, that for the heat engine, we will say that cycle, okay, for this one, 100% efficient cooling device. This one is the device. It is not a cycle, but this one should be cycle. Not possible. Okay, so now I'm going to talk about another definition of the entropy. That is, it shows the direction for spontaneous processes. Okay, so that spontaneous processes, I can give you some example. For example, that glass breaks, okay, and we have never seen that glass pieces come together and make it a total again, or any spontaneous process that flows. For example, we have here that the block slides down the inclined plane, and this is a spontaneous process because it happens due to potential gradient, and that potential gradient drives the motion. And this the spontaneous processes has one direction, and that is determined by the second law of thermodynamics. Now we will see how it happens. Say that I have a block here and it slides down. Okay, good. Now this opposite motion is impossible by the second law of thermodynamics, but it is possible from the first law of thermodynamics, because at the end what happens is that when it drops, this block has given its energy to the environment. So it has a change in energy of mgh. That mgh becomes the delta U of surroundings. And this equality doesn't put any direction. So you cannot see any direction here that this one cannot happen, this one cannot happen. So this is just a balance. Here, if you have 100, we have talked about this one, it should be 100 too. That's all. If the numbers are okay, the process can happen. Now what I want is that from first law principle, I want that I have this amount of energy now in the environment, I want it back, but in this manner. So is it possible that this block can rise itself without any work that is supplied by the environment? Is it possible? Now we will analyze it. Okay. So before analyzing it, I will just write the required quantities here. And when the block drops, at the beginning it has an internal energy in the amount of the U initial. Okay. And then it drops due to friction, the temperature increases, and that temperature increase that is shown as the part of the internal energy of the block here. The block internal energy increases. Okay, that is due to friction, and that is converted into heat. That heat is dissipated as the internal energy of the block. So if I write the first law for this block, what will I have is that, and I assume that this is adiabatic block plane system. Okay, it is together. So what it means is that I can have heat transfer between this block and this plane, but from this plane and the block to the environment is not considered. This is not a higher order approximation. This is a good and a valid approximation for this process, because whatever energy is given from the block, it becomes the internal energy of the plane here. So in that case, if you know the first law of thermodynamics, it says that the sum of kinetic energy and the potential energy of the internal energy of the system, it should be equal to that in minus out. This is the first law of thermodynamics. And for this process here, there is no heat transfer. The system, I have said it, block plane system. It is adiabatic block plane system, because this block with that plane, it is always my system. It is always. It's always my system. And this block plane system will have a different kinetic internal energy at the end. They will have a different potential energy at the end. Kinetic energy is not considered here. And the in and out quantities are zero, because there is no heat transfer, because we have said the system is adiabatic, and we don't have any work transfer here. Okay? There is no work done on the system. There is no work done by the system on the environment. It is just this change of the block position. And the system boundaries change. The elevation change. It moves in different elevation. Therefore, that delta U, we can write it as delta potential energy of the system will be equal to 0. And the U final minus U initial will be equal to mg. And instead of that, so that it will be negative, but I put the negative inside the brackets. So it will be that the Z final, so negative Z final plus Z initial. Okay. Initial height minus final height. In simple terms, it says that, as I've said at the beginning, that this internal energy change of the system and the block plane system is equal to the change of potential energy of the block itself. This one's for block. This one's for system. Okay. Now let's suppose that we are trying to get the opposite one possible, and we are trying to see that if the opposite one is possible from the second law of thermodynamics. Now let's see that. To understand it, so I will have three processes. The first process is that the block rises to the top spontaneously, getting its initial properties. This is the first process. Okay, so I will have the processes here. This is the first process. This is my block. Okay, and it has an internal energy of U final and also the potential energy, and it rises. We don't know it is possible or not. We are trying to check it. It rises here, and the U final becomes U initial. Okay, and then I want to make it a cycle. Okay, this is not a cycle yet, and I want to make it a cycle. This is the first part of the cycle. Okay, first part of cycle. This one rises. The next part of the cycle comes. That next part of the cycle is that this block is lowered from top to the bottom at the same internal energy. So I'm using some additional work, for example, pulley system or somebody from the environment. It takes it from U initial and to put it back here. And it is there with U initial, same U initial, but there is work done on it. Okay, and this one is by process the second part of cycle. Okay, you see that this one rises. This one is spontaneous. Okay, this one is by additional means. Okay, for example, it can be pulley system. Okay, or the anyone, okay, someone. And it applies some potential energy on it and lowers it down. Now comes the last part of the cycle. We transfer heat to make the internal energy back to the previous value. So let's do that last part of the cycle. in that last part of the cycle, so we should get the cycle back. You can see that first part of the cycle is U final, but now it is U initial. So what I do is that I get U initial and give some heat, Q. Okay, the Q in, this Q in will make the process as this U initial. Let me write it out of the block here, that you can see what happens. As a transfer of heat, U initial rises to U final. And cycle complete. Okay. This is a cycle, you can see it goes there and back here and here. This is a cycle. So the cycle has three processes. One, it rises spontaneously to there, and then some additional means lowers it down, and then last part we give it heat to make it to U final again. So this is the how cycle goes on. Okay. Now let's see what is the problem here. And is it violated? So because this one is impossible, it cannot happen. This is impossible. We should see from the second law principle. Okay, but from the first law principle for this cycle, okay, first law for cycle. What is that first law for the cycle? Delta U is total in minus total out. Okay. Delta U of system, block plane system, and the plus delta kinetic energy, you can add it, and plus delta potential energy. Okay, the cycle starts at point U final, and ends at U final. It starts the Z final and the Z final, velocity final and the velocity final. Therefore, for this cycle, this part is 0. 0 for cycle. Because initial properties is same as final properties. Okay, this is 0 for the cycle. Now comes the left and the right hand sides. So we have one heat transfer to the process, which is Q in. There is heat transfer to the process, Q in, heat addition to the process, and there is work transfer to the process, because some additional work, by additional means, it takes this one from there and put it back. So it should be that work in is equal to 0. Okay, so then I can write this one as, so Q in will be equal to negative work in. Okay. That is the principle. And instead of negative work in, this negative work in is exactly the same as work out. Okay. Because that negative, if it is negative work into the system, it means that it is work out of the system. That's all. Okay, and this is the final result that I have got. Okay. And now let's see what is the problem with that cycle. And let's see, there is I can think of this one as heat engine, because this is cycle, and I think this one as a heat engine. And there is a heat engine that works, that is not like this one, but there is a heat engine that works with Q in that's equal to work out. That's possible. So this heat engine is there, and for that heat engine you have the Q in, okay, and then you have the work out, and this one is not there. There is no QL, so it is impossible. Because let's go back to Kelvin-Planck statement. Kelvin-Planck statement says that it is impossible to build an engine that will operate in a cycle. So there cannot be a cycle that will give a net amount of work with a source of single reservoir. So you cannot have a source with a single reservoir. You see, that is the impossibility of the process. So therefore, in one of these systems, there is a process that cannot be possible, which is by experiment, this one. Okay. So why don't you say that, for example, this one is not impossible, this one is not impossible, but this one? Because the second law is not that is theory. It is experiment. One of these by experiment is impossible, and that is spontaneous processes. That's all. That's what second law says. Good, and this is the direction for the spontaneous processes. Now comes another important result from the second law. That important result is that reversible processes. Add it here. And reversible processes is used for idealization, okay? And these are the ideal processes that will, you know, that you can reverse it back. Let's say the process goes in that way, let's say, and it can be reversed back, but reverse it back, but this is the condition that there cannot be any change in surroundings, there cannot be any change in the system. It should be perfectly reversible. It is like that you are going to some place, but nobody knows that you are going there. And you are coming back and nobody knows that you have come back. Okay, you don't leave any trace on the surroundings. That is the reversible process, ideal process. You should get it, ideal. Because no process is reversible. In every process, you are leaving some, you know, that sign on the surroundings that this process has occurred. There is no reversible process. Every process is irreversible. And the irreversibility we will see in the next slides, that friction and the potential difference, etc., creates an irreversible condition. But there is a simple reversibility that may happen, but there is no, as I said, you can approach it. This is ideal. Okay, you can approach the ideal conditions, but you will not get the ideal condition. So this one is the pendulum here, and this is inside the vacuum. And inside the vacuum, there is no friction against it. And if there are also, you can see that here you have the bearing system, and for this bearing system, no friction here. Okay, so no friction in the mechanical parts. Okay, even if there is no mechanical part like a bearing, say that you have the string, and that string must not also create a friction here. So no friction and no air and perfectly vacuum. This is not the vacuum, but perfectly vacuum. And the absolute vacuum. And under these conditions, what will happen is that the potential energy change of the pendulum will be converted into kinetic energy change. So you will not have any loss. So the mg del h will be equal to mv squared by 2. Okay, that is the conservation of mechanical energy. And in this condition, it is reversible. You can see that it goes there and comes back there. It goes there and comes back there. You can see that it doesn't change its position and its elevation. It is always at the same elevation. And it is what we call as reversible. Okay, it is reversing at the same conditions back. But as I said, there is no reversible condition in life. There is one more reversibility limits. So here we have 40 degrees Celsius water. And for this water, and the environment is at 20 degrees Celsius. Okay. And there is a finite temperature difference between this one and the environment. Environment is at 20 and the water is at 40 degrees Celsius. And after some time, they will get the equilibrium conditions, and this process is also irreversible. Okay. And again, the irreversibility comes from the principle of the second law of thermodynamics. The reason is, I will give you just one example. Say that this one is 40 and this one is 20. At the end of the process, let's say they got 28 degrees Celsius. Okay, what you should do, and you should use some external device, some heating, and you have to increase this one to 40 back. Okay. At the same time, for other device, you have to use some cooling, okay, and get it back to 20 degrees Celsius. Okay. These are the two processes that you should do. Okay, so what we can do is that for this process, to get it easily, we can put a refrigerator here. Okay, that refrigerator, what it will do is that it will take the temperature of this 28 degrees Celsius here to 20 degrees Celsius. It will cool it, and the heat that is transferred from 28 to 20 degrees Celsius, okay, that the heat that is removed, okay, Q. Okay, let me show with a diagram here so that you can understand what I mean here. So I have a reservoir here, I have another reservoir here, okay, and one of the reservoirs will be at 20 degrees Celsius and one of them will be at 40 degrees Celsius. Okay, and I'm using refrigerator here. That refrigerator, it was initially at 28. It drops temperature to 20, and by removing the heat from it. And here I have the refrigerator. And that refrigerator removes rejects that removed heat from this object to another one, and that another object increases its temperature from 28 to 40 degrees Celsius. You can see it is a very perfect device. If you remember the working principle of the refrigerator here, you can see it gets low temperature source and removes to a high temperature source. From, in our case, it was 28 and it is dropped to 20 degrees Celsius. Here it is 28 and it is increased to 40 degrees Celsius. You see it perfectly balanced and everything gets back. But the problem here is that, you can see, let me go back to here, the Clausius statement. It says that it is impossible to build a device that will transfer the lower temperature thermal energy to higher temperature without any work input. But that is the deadlock that we are in. So this device will need some work in. Okay, you see, the energy, the heat energy that has left the system will never come back. Okay, this one will need some work in, and that work in will be additional work from different than QL and the QH. Okay? And therefore, this one is irreversible process. Okay. But we can make it reversible. Okay, how can we make it as reversible? Let me erase this part and write there. So we can make it as reversible. How can we make it as reversible? This one can be that by providing a temperature difference in the amount of dT. Okay, so it is, this dT amount is, very, very small. It is approximately 0. Okay, so then why in this condition it becomes that reversible? Because the environment, this is your system that it cools, and this is the environment. The temperature difference between your system and the environment is so small that reversing process is very easy. So that process, cannot detect the direction. So the temperature difference is so small that the process itself cannot detect some direction. And in that way, it will be reversible. And the properties will be uniform everywhere. So it will be uniform everywhere. Okay, and next comes, this one has become 40 minus dt and 40 minus 2 dt environment. 40 minus, you can see always the dt temperature difference, and it goes till infinity. Okay, infinite time. So that is the problem with the reversibility. If you want the process to be reversible, you will need infinite time. That is the one problem. And the second problem is that heat transfer needs area. So you can see that heat exchangers are very large. There are lots of zigzags and there are lots of fin that is placed in that heat exchanger to make the heat transfer process easier. This is like work is not like that, but it is lazy stuff. This one is lazy. And you will need for this process infinite area. Okay. And infinite area, infinite time, and you will get the reversible process in this limit. That is impossible. Okay, but we have two types of the reversible processes. One is externally reversible. It doesn't leave a sign on the environment. For example, here you have the small temperature difference. And the one is that internally reversible process. And in that case, the process itself, here it is frictionless, for example. Frictionless, and there is no any loss due to the work done. This one is internally reversible processes. But for thermodynamics, when we say that internally reversible process for heat engines, okay, and also for refrigerators. For heat engines and refrigerators, when we say internally reversible process, in the implicit meaning is that this one is implicitly. Okay, it also means that totally reversible. So the reason is that the thermal reservoirs and the surroundings, so this one is not immediate surroundings. This is the surroundings that is beyond the immediate surroundings. They don't have temperature change. And the temperature change, and also they don't have that is change in internal energy so much, okay? Because these are very large. Okay, very large systems, because the thermal reservoir and the surroundings are very large. Therefore, these two are reversible. And since this one is reversible, the system itself is internally reversible, and therefore when we say that internally reversible system for heat engine or the refrigerator systems, and it means that it is implicitly totally reversible. That is the definition of it. And the irreversible processes, what are the reasons for any irreversible process? That it means that you will have a difference in potential, but this difference is finite, unconstrained, or partially you can say that finite difference. Okay, and if you go back to here, for example, heat transfer, you can see there is a finite amount of heat transfer. And another irreversible process, why the process is irreversible, because, and the characteristics of the irreversible process is that they have a finite rate, but irreversible processes infinitely slow rate. Why infinitely slow rate? Because potential difference is very small. And you can think this one as there is a temperature difference of delta T. Here you have a temperature difference of dt. And for this temperature difference, the heat transfer needs lots of time, and therefore it goes very slowly. Here you have the delta T temperature difference, and therefore process has some speed. And there has a definite direction for it. It goes that in the decreasing direction of the gradient. So if it is the potential energy should decrease. If it is voltage, voltage should drop. If it is pressure, pressure should drop in the direction of the drop of the gradient. But for the reversible process, there is no direction. So the process may go in that direction, may go in this direction. There is no directionality. It can select any two directions because the potential difference is very small. That potential difference is very, very small, such that the process itself cannot detect the direction to go. So, for example, that mgh, that is potential energy, this potential energy difference tends to 0. Therefore, that this block cannot decide whether to go down or whether to go up, because this one is very, very small, and therefore you don't have any directionality. The system doesn't pass through equilibrium states. However, final and initial states can be equilibrium. This one is also a continuous set of, and this one means that, let me elaborate this one more. Say that I have a piston cylinder device here. Okay, and here you have 40 degrees Celsius, and here you have 0 degrees Celsius. And during the heat transfer process, it is possible that here you have that 38 degrees Celsius, and here you have 30 degrees Celsius, very close to the environment. You can see these parts are very close. Here you have lower temperature, but the temperature needs some time to propagate into the domain. Okay, the temperature doesn't have an infinite, that is, we can say, conductivity. Conductivity doesn't have infinite speed to propagate into the domain. It has some finite speed. Therefore, the boundaries that are close to this 0 degrees Celsius phase temperature much better than the points that are away from this one. Therefore, inside the material, you have the gradient. Here you have higher temperature, and here you have lower temperature, and therefore it is not in equilibrium. But for the reversible processes, you should always have the uniformity. Why? The reason is that for uniformity, because here you have that, for example, 20 plus dt, and here you have the 20. And since the temperature difference is so small, and therefore you will have the uniformity. All that is, these are not perfectly uniform, okay? But these are them. You should remember that these are all imaginary stuff, okay? Imaginary. And some people, that argues that for this imaginary stuff, I use my brain. And if I use my brain, I spend some energy, and therefore there cannot be a reversible process. Because for that reversible process, I use my brain, additional source. So these are, these are under argument or discussion, but at the end, they give some clues. There are lots of benefits of these reversible processes. Anyway, you have 20 plus dt, and here you have 20 degrees Celsius. Since the temperature gradient is very small, everywhere you will have approximately the same temperature, which is the 20 degrees Celsius. And the change in the state is required to reverse the process. We have talked about this one. No change in surroundings. And the quality of energy is reduced, but quantity is conserved. This is first law. First law is always true, but in second law you have the generation. It is not conserved property. Second law is not conserved, but for the reversible ideal processes, both of them are conserved. Okay, why do we have the irreversibility friction? That is free expansion. For example, explosion of balloon. Let me give one example here. Free expansion, you can see that unrestrained. Heat transfer and the current flow mixing. This one is also an irreversible process. And therefore, the turbulence is irreversible, but laminar is reversible. So I can give you one example. For laminar is reversible. We saw that what is the reason for these processes? If it is friction, you have the force difference. If it is expansion, you have the pressure difference. So friction, you have said it, if it slides down, there is a force difference between this one and that one. That force difference may be in equilibrium and or it can accelerate anyway. So you will have that friction effect. You will have that pressure, temperature will drive heat, and voltage will drive current, and chemical potential will start the reaction. And examples can be that drag, interface of fluid, solid, fluidic motion, paddle wheel, explosion of balloon, and the thermal communication, electricity flow, and the diffusion. Okay, there are two important results of the reversible processes, and the one is that two engines operating between the same thermal reservoirs, this one is important, will not have the same efficiency. Reversible one will be always greater than irreversible one. Second one says that if you have two engines between two same, as always with this first one, you have TH here and you have TL here. It doesn't matter, you put reversible engine 1 here or reversible engine 2 here, even reversible engine 3 here, whatever you put between these two thermal reservoirs, you have the same efficiency. Reversible 1 efficiency is same as reversible 2 efficiency, the same as reversible 3 efficiency, and etc. Okay, these are the two important results of the Carnot principles. And in other words, it means that ideality is the limit. You can approach it, but you can never get it. And the Carnot cycle, it is a reversible cycle, and it has 4 processes. One is that reversible isothermal process from 1 to 2 is reversible but isothermal. All of them are reversible. Then you have the reversible adiabatic, and we have the reversible isothermal and the reversible adiabatic expansion. This is the Carnot cycle, and for this Carnot cycle, and there is some problem here. So this one should be not expansion but compression. You have that reversible adiabatic compression. Okay, for this Carnot cycle, there are 2 questions here. The first one is, can 2 isotherms cross if extended? So that I have one isothermal line like this one, another isothermal line like this one. So this one is T1 is constant, this one is T2 is constant. The question says, can these 2 isothermal lines cross each other? If it is possible that you have something like this one, of course no, because the substance or material at a point can have 1 temperature only. It cannot have 2 temperatures. It cannot cross it. Therefore, it is impossible. And the next one says that, can reversible adiabatic lines cross if extended? You will see that the first one, the isothermal lines cannot cross each other because here you have that temperature, okay, that defines the isothermal lines, and that temperature at one point, okay, can have 1 value. Okay, that is the temperature definition. It asks again that the reversible adiabatic lines, is it possible that they can cross each other? And you will see that in the next slides, it is also impossible, because this reversible adiabatic lines is another stuff that is called isentropic lines. Okay, and isentropic lines is the lines you have that entropy is constant. Okay, constant entropy, and that constant entropy lines cannot cross, similar to this one, because at one point you can have one entropy value. At one point you cannot have two entropy values. That is the definition for the isentropic lines. Therefore, two important results from Carnot principles. And here you have reversible adiabatic lines from 2 and 3. We have the reversible adiabatic lines from 4 to 1. If I extend the lines here, is it possible they will cross each other? Of course, no, because they are isentropic lines. Good. Similarly here, isothermal lines 1 to 2 and 3 to 4. These lines cannot cross 2. These are isothermal. Okay. And the second couple of lines, these two are isentropic. Good. Okay, now before moving on to the definition of entropy, I will tell one more stuff, which is that point function, or it is also called that state function. Okay. One definition of it. So there is a person that travels along this path here, and it travels from point 1 to a meeting location here, and then from that meeting location comes back. So if I ask the change of displacement or the change of location, it will be 0. This person has 0 displacement because it has come to its initial point, and since that x initial is same as x final, displacement is 0. But if I ask that work that she has consumed during this travel, the work is not 0. You can see the two actual differences. In one case, we have that displacement is 0, however, the point is there. We have the same point as the beginning, but the work is not 0. So this is called the point function. Okay. The functions that are defined at a point, and for all of the point functions, it is independent of the path. So for example, this person can take something like this one. Okay. Or it can take something like this one. Or it can take something like this one. Okay. Or it can take something like this one. Okay. However, path it takes, the displacement is 0. But what about the work? If you look at the work, for all of these cases, work at 1 is not equal to work during 2. That is not equal to work during 3. So all of the works are different. Okay? And this is the path function. Okay? And it depends on the path. But this one is independent of the path. Independent of path. And one more property function can be, for example, the volume. So you have the initial state and the final state and the initial state. The volume changes 0. For example, internal energy changes 0. And at the initial state, if you have T1 and then T2 and then T1 back, and delta T is 0. If you have P1 and then P2 and then P1, you will have delta P as 0. You can see all of these properties are getting their initial values and changing properties, of course, 0. But if I look at the work is not equal to 0. If I look at that heat is also not equal to 0. And the heat transfer, work transfer, the mass transfer, they're all dependent on the path. Therefore, it is called path function. You will see in the next slides that entropy is also a point function. And the change of entropy will be 0 for this process. That is a property. So let's look at the derivation of the entropy, and this will be a very important equation that we will use for our next slides. Okay, we have a high temperature source with TH, and that high temperature source gives energy to a heat engine here, that heat engine provides us with a work of reversible work. Del work reversible, you can see it is reversible. And then it gives its rejected heat to a device here, piston cylinder device. And there is a temperature here, which is T. And then you can see there are two reservoirs. So you have that TH reservoir, and you have that T reservoir. But this T reservoir, it may have the change in value of the T, can change. And then you have that, see, yes, you have that temperature to a T reservoir, and then from that T reservoir, there is a piston cylinder device that provides the work of the system. Okay, this one is that reversible, this one is under question mark. If you look at the overall picture of this one, you can see there is something problem which violates the Kelvin-Planck statement, that you have one source of heat and you have work, but no source, no sink actually, no heat rejected. So that violates the second law of thermodynamics. Okay, now if I want, so there is that this one means that, so violates second law, okay, which is Kelvin-Planck statement. This is the first step. And if I go back to the Kelvin-Planck statement, if you remember it, it says that, so it's impossible and will give net amount of work. So you see that it cannot give net amount of work, positive work. You see, this one is positive. And now for our case, let's see that problem in our case. For the case here, you can see that this violates, and therefore del work reversible plus del work of system out and out. These two cannot be positive quantity because it violates. Therefore, they are either equal to 0 or less than 0. This is the first step. Okay? And the second one is that I will use the Carnot efficiency. And if you remember the Carnot efficiency, and the Carnot efficiency says that actually it can be Carnot efficiency, but for that, okay, it is okay, the result of it, we can say it. So it says that TL divided by TH is equal to QL and divided by QH. I will use this one. For this process here, you will have that T divided by TH should be equal to del Q and divided by del QH. Okay. This is the process for this one. Okay. Now I have this second. I will use these important rules in my derivation. But before that, let me write the first law for that cycle. Okay. And the first law says that for this one, so changing energy of the system can be total energy, dE. So dE means that it is du plus d kinetic energy and the plus d potential energy. It will be equal to in minus out. Okay, and the dE will be equal to, that is in. We have the in, which is del Q H, and this one is the in, minus that work, which is reversible out, the first one, minus del work and the system out. Okay. And I have forgot one thing to add here is that for the properties, for the point functions, we can see that you start at some point and you travel back to the same point, it gets 0. We have talked it. And to write it, we use this cyclic integral. Cyclic integral means that some cycle has happened. We have got start and get it back. And for cyclic integral of dx here, it will be 0. For cyclic integral of dv, it is 0. For cyclic and du is 0. So all of them, dt and the dp here, it is 0. And the entropy, I will show the entropy in next slides, but ds is 0. But for cyclic integral of the work, it is never 0. But for the cyclic integral of heat, it is never 0. So you will have the cycle. This one shows that it is cycle. You can see this one is cycle. It goes and it gets back. For the cycle, the property point functions are 0. But for a process, it is not 0. For a process function, it is not 0. It depends on the path. Okay. So this one is clear, I think. Okay. Now what I will do is that I will replace this del QH from that one. So from here, I know that del QH is equal to that del Q multiplied with TH, that one divided by T. Okay, let's do that. So you will have that dE will be equal to, instead of that one, I will write that del Q, and this del Q, you should remember that this is out quantity. Okay, and del Q and divided by that T and multiplied with TH. And that one minus del work reversible out and the del work system out, and let me write one by one, del work system out. Okay, so what I will do now is that I will take the cyclic integral of, okay, so what I will do now is that I will let one cycle to happen. Let one cycle to happen. Okay, and I will let one cycle happen, and then I will take the cyclic integral of all of the terms here. So del dE will be equal to that del Q multiplied with TH and divided by T minus del work of reversible and the system. I will write this one as that. Let me write it one by one. Del reversible out minus del work and the system out. Okay, and if one cycle happens, take cyclic integral. Now I will take the cyclic integral to see what happens. So for this one, for that one, for this one, and for that one. And we know that dE is the sum of, this one is sum of du and the d kinetic energy and d potential energy. Okay, and all of them are point functions. Okay, therefore this one goes to 0. And now comes the next terms. I will write this one as TH multiplied with del Q divided by T will be equal to del work reversible out plus that del work system out. And I know that TH is the reservoir. It is fixed temperature, okay, but T can change. This temperature value can change, but this one is a reversible, the reservoir temperature, and therefore this one is constant. Okay, and this is since reservoir. Okay. This one is not a reservoir. Therefore, you will have that TH out of the bracket. You will have the cyclic integral of del Q by T. That one will be equal to this cyclic integral. It will give you reversible out, and this one is total, and the reverse system out. Okay, good. So you will have that work total. And this work total will be equal to that TH and del Q divided by T. What does the Carnot efficiency, the Kelvin Planck statement says? This one cannot be positive. It is either 0 or equal to 0. So this quantity TH, therefore del Q by T is either 0 or less than 0. Okay, and since by Kelvin Planck statement that work total out cannot be positive, it can be by 0 or less than 0. Okay, then it comes, the final result is this one. Okay. And since TH is constant, actually this is not a final, I will make one more final step here. And the TH is constant, then you will have that del Q by T. This is the final result, and this is called Clausius inequality. Okay, and I will use one more approximation here. That approximation will be that. So I will let that system also be reversible. Okay, so that this one was reversible, the first one. This one was reversible. Now I let the work of the system to be reversible. In that case, I will have that work total reversible. In that case, it will be equal to that del Q by T and TH here, of course. Let me erase that one, write it clearly. Del total reversible will be equal to that TH multiplied with del Q by T. Okay? That if the system is reversible, now it becomes the totally reversible. But now you will have this inequality problem. If it is reversible, the cycle can run in that way. It can also run opposite to that one, since it is reversible. And if I allow that work total, let me write it clearly here. If I allow that work total is less than 0, okay, in one direction, for example, for this one, it will be okay, but in the opposite direction, work total will be greater than 0. But for the Kelvin-Planck statement, it is impossible, because this one violates second law. It doesn't matter whether it is reversible engine or irreversible engine. Any device that violates second law, that's all, it's finished, okay? Therefore, we cannot have positive work output in opposite one. It will be always either negative or 0. For irreversible ones, it will be negative because you cannot reverse it. But reversible ones, if you reverse it, cannot be positive on the other rotation or on the other direction of the cycle. Therefore, if it is reversible, work total is always 0 due to Kelvin-Planck statement. Okay. And this Clausius inequality is for anyone, but if reversible one, then it means that this quantity here cannot be less than 0. It will be always 0, and cyclic integral of del Q by T is always 0. Okay, for the reversible ones. And let's go back. So cyclic integral of some variables are 0. These are called the point functions. And for this one, del Q by T, I can write this one as some quantity. D means differential or differential, okay, of some quantity here, some variable property. Okay, that is equal to 0. In cyclic integral of change of some variable property is equal to 0. And that property, this property here, is del Q by T, but we can give it some name. So that name is what we remember is that it is entropy. Okay. For that entropy, for reversible processes, that is how we derive the entropy. Okay. And so the name is entropy. Okay, this is the entropy, and by using these relations here. Therefore, entropy is that del Q by T, and that is ds. Okay, with this one, I finish the introduction to entropy, and in the next lectures, I will use this final relationship here and derive the important relations for the entropy chains of pure substance.